Hello and welcome. Today we're doing a question from LeetCode 75. It's called Successful Pairs of Spells and Potions. So what is this question asking? You are given two positive integer arrays, spells and potions, of length n and m respectively, where spells of I represents the strength of the ith spell, and potions j represents the strength of the jth potion. You are also given an integer success. A spell and potion pair is considered successful if the product of their strengths is at least success. Return an integer array pairs of length n, so this is the same size as our spells over here, where pairs of I is the number of potions that will form a successful pair with the ith spell. So example 1, we have spells length n and potions length m. We want to return an output also size n, the same as spells, of the number of potions when multiplied with our spell that will be greater than equal to success, which is 7 in this case. So we go ahead and multiply 5 with 1, 2, 3, 4, and 5. 4 of them are greater than equal to 7, so it's 4 over here. Then with 1, none of them are actually greater than equal to success, so this is going to be 0. And for 3, when multiplied with 1, 2, 3, 4, 5, 3 of the products, 9, 12, 15, are greater than equal to 7, so we have 3 over here for a final output of 4, 0, 3. And same thing with example 2. We have 3, 1, 2, and 5, 8, 5. So 3 multiplied with 8 is 24. Then with 5 is 15. With 8 again is 24. 2 of these products, so 24, 24, are greater than equal to success, which is 16. Then with 1, none of them are greater than success. And with 2, only 2 of the products are greater than success. So our final output is 2, 0, 2. And we have some constraints over here. Okay, so the ask is pretty straightforward, right? We just want to see the pairs between cells and potions that will be greater than equal to success. So say we take a look at example 1 again. We have 5, 1, 3 for our spells and 1, 2, 3, 4, 5 for our potions. The brute force solution that comes to mind, right? The intuitive approach is just to make every single pair. So if we were to loop through, the first spell we would see is 5. And for this spell, we just want to loop through all of our potions and see which product is greater than equal to 7. So first, right, we check 5 and 1. That's equal to 5. It's not greater than equal to 7, so our current successful product is 0. So 2 times 5 is 10. It's greater than equal to 7, so this is a successful pair, which means we have 1 so far. Now, all these others, right, these are numbers greater than 2, so these are all going to be successful as well, because if 5 times 2 is greater than equal to success, any other greater number when also multiplied by 5 will also be greater than equal to success, which means right now we have 4 total successful products. And we would just repeat the same thing for 1 and then 3. So what is the time complexity going to be for this solution? Remember, we have n elements in spells and m in potions. Well, basically what we're doing is looping through n, and then for every single spell, looping through all the potions. So we're going through potions, which is size m, an n number of times, which means our time complexity is going to be n times m. Is there any way to improve on this? Any way we can cut down from checking every single pair? Well, if you notice, right, when we had spell being 5, we didn't actually need to check every single pair. Once we got to 2, because they were already sorted, we didn't need to check the remaining numbers. We knew those products would already be greater than equal to success. So what we can actually do is just go ahead and sort our potions. This will be a one-time operation, and the time complexity for that, if potions is size m, will be m log n. Now all we need to do once this is sorted is go through our spells and look for that first number when multiplied with spells that will have a product greater than equal to 7. So this is going to be a binary search for every single spell in spells. So what would that be time complexity wise? Well, for every single spell, we know there are n spells in total. We're going to be doing a binary search on a sorted array. Now this is size m. A binary search would be log m, and we'd be doing this n times. So the total time complexity for this would be n log m. So first we do our sort, which is m log m, and then we do a binary search for every single spell. So that would be n log m. Now, is this really better than n times m? Generally, yes, specifically for large inputs. And we know in our constraints, we have some pretty large inputs, right? N and m could be going up to 10 to the power of 5. But say we had just one spell and then 100 potions, we would sort that input of 100 and then perform a binary search on it. But that wouldn't necessarily be better than just multiplying and just making 100 checks. So there are some cases where this brute force approach would be better, right? Just making checks, don't bother with sorting. But in most cases, and because our inputs can get that large, if we look at all the test cases we're going to be working with, this is generally going to be a much better, more efficient solution. So now that we know what we want to do, let's go ahead and code this up. Okay, to code this up, the very first thing we want to do is sort our potion. So it's going to be potions.sort. And we know we're going to have an output array the same size as spells. So we want to go ahead and initialize that as well. So I'm going to call that pairs, and it's going to be empty. Now say our example is the following. We have 3, 1 for spells and 6, 4, 3, 2 for potions. Success is going to be 7. Right now what we've done is gone ahead and sorted potions. So instead of 6, 4, 3, 2, it's now going to be 2, 3, 4, 6. And we also have pairs, which is going to be empty. Now what we want to do is loop through our spells. So for spell in spells, what do we want to do? We want to look for that first number in potions when multiplied with our spell that will be greater than equal to success. So this is just a classic binary search problem. And anytime we want to do a binary search, what do we want to do? We always need a range, a low and a high. Because how a binary search works is we search within this range and then modify one of these ends to be smaller. We're just cutting it in half every single time, but we do that by moving one end of the range in. So we always need a range for this, right? So for our range, it's just going to be potions itself. So low and high are going to be 0 and length of potions. So low is going to be 0 and high is going to be 4 over here. It's not in an index just yet. Now, while they don't meet in the middle, while the range still has numbers within it, so while low is less than high, we want to look for the midpoint of that range. So mid is going to equal low plus high, integer divided by 2. So low is 0, high is 4, 0 plus 4 is 4, integer dividing that by 2 is 2, which means mid is going to be 2. So index 2 is this over here. Now, we want to see how that midpoint relates to what we're looking for. So what we want to do is check the potion we have at this midpoint. So if potion at mid, so 4 over here, times the spell that we're on, so 3. So if this is greater than equal to success, what do we want to do? So right now we know that we have 4 over here. 4 times 3 is going to be 12. That is greater than equal to success. So what we want to do is move our high point down to mid. So high is going to equal mid. Because remember, we're looking for that very first number that is going to be greater than equal to success. And if that's not the case, so else, meaning potion of mid times spell is less than success, we want to move our smaller range up past that midpoint. So it's going to be low equaling mid plus 1. And why plus 1, right? We already know mid is going to be less than success in this else case, and we don't want to stop there. We want to look for that very first number that's going to get us to be greater than equal to success. So we're going to move past mid. So right now in this first iteration, what do we have, right? Potions of mid is 4. 4 times 3 is 12. 12 is greater than equal to 7. So what we're going to do is move high down to mid. High is now at index 2. We go back in this while loop. Low is still less than high. We calculate a new midpoint, which is 1. And we make the same check again. So 3 times 3 is 9. It is greater than equal to success. So again, we're going to move high to mid. So high is now at 1. We go back in this while loop. Low is still less than high. We find the new midpoint. So 0 plus 1 is 1. Integer dividing that by 2 is going to put us to 0. We don't care about decimals. And we want to make the same check, right? Potion of mid is 2. 2 times 3 is 6. It's not greater than equal to success. So we're in this else condition, and what we do for this is just move low to be mid plus 1. So low and high are now both at 1, which means we can exit this while loop, and we know this index marks that first potion that is going to be greater than equal to success, right? Index 1 right over here, 3 times 3 is 9, greater than equal to success, and every number after this is also greater than equal to success. So how many total potions will be successful when multiplied with 3? Well, we're at index 1 right now. The total length of our potions is 4. And we know 3 of them are good potions. So all we really need to do is 4 minus the index we end up on to get the number of successful potions. So once we're out of this while loop, all we need to do is append to pairs. So pairs.append length of potions minus low. Low or high doesn't matter. They're both going to point at the same index. And in the very end, all we need to do is return pairs. So we are going to return pairs. We have 3 successful potions for 3. And just to finish out this example, right, we just completed 3. We had 3 successes over here. If we go back in our for loop, our new spell is going to be 1. We're going to be setting low and high again. So it's going to be at 0 and 4. And while low is less than high, we find our midpoint. Midpoint is 2, so potions at 2 is 4. 4 times 1 is 4. It's not greater than equal to 7. So we go in this else over here and we move low to be mid plus 1. So low is at index 3. We go back in our while loop. Low is still less than high. We find the midpoint again. 3 plus 4 is 7. 7 integer divided by 2 is going to be 3. And we make a check again. 6 times 1 is 6. It's not greater than equal to 7. So again, we move low to be mid plus 1. So now low and high point at the same index, which is index 4 over here. It's not an actual index in our potions. It's past it. So now once we go back in our while loop, we exit, low is no longer less than high, and we append to pairs length of potions, which is 4, minus where we ended, which was also 4. 4 minus 4 is 0, which means there were 0 potions that actually made a successful pairing. So we append 0 over here, and all we have to do is return 3, 0 at the very end. So let's go ahead and submit this. Potion not defined, this should be potions. And it is accepted. Now we just did a full walkthrough with this example, but if you have any questions with this whatsoever, of course, let me know down below. I will answer all of them. If this video was helpful, like, comment, share, and subscribe. It really supports the channel. And as always, I will see you in the next video.